Welcome back, folks, to Scripting for Linguists. In this episode, I have this question for us. When creating a deeply nested dictionary, which is faster, Python or Julia? And as a follow-up question, I wonder if those two languages scale the same way as I give the deeply nested dictionary more and more items to deal with. The reason I ask this is because during the past week, I've implemented this algorithm proposed by the corpus linguist Stefan Gries, who works at UC Santa Barbara. In 2022, he published this paper in Lexis, journal Lexis, Multi-Word Units and Tokenization More Generally, a multidimensional and largely information theoretic approach. And the idea is that we want to identify multi-word units, multi-word strings of words that really are just functioning as one lexical unit, that is one vocabulary thing. For example, on the other hand, those four words, on the other hand, they're four words, orthographically written at least, right? But they're just functioning as one thing, as one lexical unit. And so he proposes a pretty cool algorithm to give, let me zoom into table of contents. He proposes this pretty cool algorithm to give each multi-word unit candidate a score of how likely it is a multi-word unit. And it's based on 8 dimensions. And here they are. So we have token frequency with the idea that a multi-word unit candidate that is more frequent overall in the corpus is more likely to be a multi-word unit, or it will have a higher score on that scale. Dispersion deals with how varied, across the corpus parts, that is the text files, each multi-word unit candidate is, with the idea that the more dispersed, the higher it will be on that scale. Type frequencies, there's 2 of them here, both before and after the target word, the current word. So there's 2 there, with the idea that words that occur with more different other words will be lower on that scale. Meaning words that occur with only a few or just one other word near it is more likely to be a multi-word unit, or would be higher on the scale of multi-word unitness. And then normalized entropy. Entropy is a measure of how much chaos or how much different variability there is on either side of the target word. And that deals with frequency of the flanking words. There's 2 of them there, both entropy before the target word and entropy after. And then association, this is a word association score. Again, it's bidirectional. How predictable is the second word given the first word, and how predictable is the first word given the second word. So there's 6 down here plus the 2 up here. That gives us 8 dimensions that go into a composite score that's based, that goes into a Euclidean distance little calculation to get the distance from the origin, that is 0. You have to transform these down to a 0 to 1 scale, all pointing in the right direction, so that the higher the number within that range, the closer to 1, the more likely it is that the multi-word unit candidate will be merged into a multi-word unit. Anyway, that's the algorithm. It's pretty cool. So during the past week, I implemented this algorithm in Python, and I'm looking at one kind of foundational step in the whole process. That's what I'm looking at in this video. So to give you an idea of what I'm trying to do, what I'm trying to create, let's take a look at this. Let me zoom into about there. So what I'm trying to create is a dictionary that has basically 4 dictionaries nested into each other. You have the top level dictionary, whose keys are the file names in the corpus. So for example, here's first_file.txt. That's the first file in the corpus. And then the value of that key is a dictionary itself. And the dictionary holds the words that occur in that file. So the word "the" occurs in this file. This is a toy example, artificial example here. And so the key is the word. And then the value is a dictionary. And the dictionary has 2 items. We have pre and post. That is, what are the words that occur before "the" within this current file? And so we have "the" preceded by "in," that is "in the," and we have with the, and we have their respective frequencies. These are, again, artificial examples, just to give the idea of what I'm looking at. And then the next item is post. What are the words that occur after the? We have tree that occurs 19 times, so the tree. And we have phone that occurs 68 times, the phone, right? So we're keeping track, again, of all the words that occur in the current file, but also keeping track of all the words that occur before the current word and their frequencies, and all the words that occur after the target or current word and their frequencies. And then we move to the second file, and we do that, well, the second word. We do that for every word in each file. So the word day, for example, every day occurs. Valentine's Day occurs with, the frequency that it occurs with. Then we do that with the second file, all words and all the previous and post words. Okay, so it's a super deeply nested dictionary data structure here, holding all the information that we'll need to do all those 8 dimensions I mentioned. Frequency, type frequency, dispersion across the corpus parts, entropy because we have the frequencies. We also can get type frequency because we know how many different words occur before and after the current word. Anyway, so all the information we need to run the algorithm is stored in this one deeply nested dictionary. So, like I mentioned, I implemented this in Python this past week. Spent quite a few hours doing so, and with the personal communication here and there to Stefan to ask questions. And so let's take a look at my script that gets that one part. I'm not going to reveal, not going to share my whole script right now. Just simply the function, it's really a method I implemented on a class, the method within the class that gets this data structure, right, for the whole corpus. And here it is. So here is the top level dictionary. And then I created a dictionary for the current file on line 10. Then I pull in the current file, read it from the hard drive. I find all the words, and then I start getting the previous words and the following words. By the way, I keep track of whether it occurs at the beginning of a document or the end of a document. In my actual implementation, I actually do it by sentences, so a multi-word unit cannot go across sentence boundaries. Good. So yeah, I populate this dictionary, see all these nested dictionaries happening right in here. That's not it. Right in there. Good. And then, like I mentioned, it has kind of a follow-up question or like a secondary research question, RQ2, you might say, in academic literature. I also wanted to know what the effect on the performance is by increasing the number of files that it deals with. So I'm first going to have it deal with 1,000 files, and then I'm going to have it deal with 2,000 files, and then 3,000 files, 4,000, and then finally 5,000 files, and keep track of how long it takes Python to create that data structure. And I'm going to do 10 trials for each of the 1,000 files, meaning I'll give it 1,000 files and have it do 10 trials, keep the times. And then go up to 2,000 files, have it do 10 trials, keep the times, etc. And so that's where it happens right there between lines 41 and 43 right there. I also have it write out the number of words in the corpus at the moment that it has 1,000 files and then 2,000 files, etc. Just so I can make sure I'm getting the same results from Python and Julia. I have it do that. I also have it write out the previous words and their frequencies and the following words and their frequencies for the word day in this specific text file, just as another way of a kind of a quick way of just making sure I'm getting the same results from Python and Julia. That's what I'm doing there. Okay, so let's take a look at the results of Python. I am using Python 3.12.4, as you can see there. And here it's working on 1,000 files. First iteration, I got 5.6 million words there. It took less than 5 seconds there. And then here are the results for the word day in that specific file that I had it look in. So the word day is preceded by Valentine's 5 times, that is Valentine's Day. It's preceded by every, twice, every day. And then post here, these are the words that came after day in that specific file. Is, and, now, that's, like, that. Good. And again, the idea here is just to make sure I'm getting the same results from Python and Julia. So let's take a look at the times here. Yeah, 4.6, 4.4 seconds, 4.3 if we round up there, 4.2, et cetera, about 4 seconds. Good. Then we jump up to 2,000 files, and we get more words, 11.7 million words there. And we're getting 9 seconds, 9 seconds, about 9 seconds. Yep, good. And then we jump up to 3,000 words right there, 17 million words. Good. Now we're up to 13 seconds, 14 seconds. Getting the same results. Good. I just want to make sure we're getting the same results every time. Okay, so we do that up to 5,000 words down here. There's 4,000 words there. Now we're up to like 19 and 20 seconds there. Awesome. And then 5,000 files. I think I said words. 4,000 files, 5,000 files. Good. Now we're up to almost 29 million words that it's dealing with across 5,000 files to create that data structure. And now we're up to 29, almost 30 seconds, 26 there, 27 seconds, etc. Good. Okay, good. So the question, my research question here, right, is how does this compare to Julia? So I translated this script into Julia. Let's take a look at that now. Here's my Julia script. I tried my best to do a direct translation from my Python script to Julia. Same idea, right? I create this empty dictionary on line 6. That is the top level dictionary. And then I come into the first file and I create a little dictionary for its information, for its words there, the current file. Open it up, read in the text, get the words, get the length of the words, etc. Loop over the words. Add a new dictionary for the current word in the current file. Good. Creating a little dictionary called with pre and post items. Same idea. And then I populate the dictionaries right down in here. Good. I also write out the number of words in the corpus. Bien, or did I say bien in Spanish? I was a Spanish professor for 10 years before coming here to do computational and corpus stuff. Anyway, yeah, so I print out the number of words in the corpus according to how many files it dealt with. And I also have it print out that same result from that one file with the word day. So I can just make sure I'm getting the same results. Okay, good right there. So I wrote this out to a CSV file. And let's take a look real quick at the results in the terminal here. So this is Julia version 1.10.4 I used. And again, here is 1,000 files, same number of words in the corpus we saw in Python when we have 1,000 files that we're dealing with. Okay, we're at almost 8 seconds there compared to like 4 in Python. These results are the same. So yeah, every occurs twice before day. Valentine's occurs 5 times before day, and like that's now it's that. Yeah, so we're getting the same results, same number of words, and it's taking almost 8 seconds there. That took 6.5 there, 7.8, 6.6 there, etc. And then we can jump up to 2,000 files there it dealt with. And now we're at 18 seconds, 20, 19, etc., all the way down to 5,000. Let's just jump down to 5,000. There's 4,000. Cool. We're at 82 seconds, 77 seconds. Okay. And then 5,000 files. We're at 151 seconds. So 2 minutes and 30 seconds, right? 144 seconds, 149, etc. So I had both Python and Julia write out to a CSV file. So let's go take a look at a plot of the results with our old friend R. And let me see if I can just plot this up right this second. And let's zoom in. There we are. Make this a little bigger. Okay. So the legend's kind of small, but this top line is Julia. This kind of orange line is Julia. So on the x-axis, we have number of files. We have 1,000, 2,000, 3,000, 4,000, 5,000 files on the x-axis. On the y-axis, we have number of seconds that it took to create that deeply nested dictionary data structure. Okay, so yeah, that orange is Julia, and the green, teal, what have you, is Python. Wow, okay, wow. So number one, we see that the Python line, the green line there, is below, in all cases, below the Julia line. It's closest there at 1,000 1,000 files that it dealt with. If you remember those times, it was about 4.5 seconds in Python, give or take, and it was like 7 seconds in Julia. But wow, look at this. Julia has a hard time when you add more and more files for it to deal with. And it gets exponentially like steeper, this slope. Whereas Python is nearly flat, mostly just linear. By the way, this is a low S line. A low S is a locally based smoother line that I put on across these data points. Wow. Okay, so there you have it. Python kicked trash. Python was much quicker and didn't have this like scooped exponential like increase in time there. Okay, so let's jump back to our question. When creating a deeply nested dictionary, which is faster, Python or Julia? Python won this race by a long shot. Wasn't even close. Now the question is why? What's the deal there? Well, if we go to Python, right, and we go to downloads, we look at the source code, and you download the source code right here, like a gzip source tarball. It's implementing its dictionary in C. So the dict object.c, which I have up right here, is how the dictionary in Python is implemented. It's C code. So yeah, unsurprisingly, C is a super fast language. It's often the kind of benchmark against which other languages are tested for performance. And so unsurprisingly, Python's dictionary is super fast because it's implemented in C. So what I'm kind of concluding from these series of videos about Python versus other languages, Mojo, Julia, I haven't tried R. Maybe I should try some R with C++ with the RCPP package, is that when somebody says language X is faster than language Y, you have to say, wait, in what task? What benchmarking task did you do to claim that? Because we see here that because Python's dictionary is implemented in C, it's super fast. So some task that is dictionary heavy will be fast in Python because of this fact. So yeah, just be a critical thinker when you hear language X is faster than language Y. You have to say, in what benchmarks are you basing that statement on? With a lot of corpus linguistic techniques, right, which use frequencies of words, many words, which therefore use dictionaries or hash maps or associative arrays, Python's quick because it's implemented in C. So there you have it. Go Python/C. Yeah. All right, so to conclude, we say that Python is awesome. Python is the workhorse, at least my workhorse, for corpus linguistic methodology and techniques and computational linguistic techniques, right? Python is an awesome language. Again, I've seen in previous videos, I'll link to above and below, that Julia was faster than Python when finding the collocates of node words. But by and large, yeah, if it's a dictionary, if you have a dictionary heavy task you need to do, Python is awesome. I'll say that. Well, great, thanks for watching, and see you next time.